Okay, in this lecture, we're going to learn about phase changes and heating curves. Previous lectures, we talked about intermolecular forces, van der Waals forces, dispersion forces, hydrogen bonding, ion dipole, and it's all these intermolecular forces that govern phase changes. And so here we have a diagram for the energy of a system. You can think of water, the melting, the vaporization, or the condensation and freezing. You have sublimation and deposition, all these terms that describe the various changes in state amongst these various phases of matter, solid, liquid, or gas. And so conversion from one state of matter to another, by definition, is called a phase change. And we know we need energy added to the system for some of these, or released from the system in others. And so the first thing I want to point out here are these terms endothermic and exothermic that we often associate in chemistry with the release or the absorption of energy in a chemical reaction. But it's not just a chemical reaction, it can be a change of phase. This is not a chemical change, this is a physical change, but we still use these terms. And some of it's counterintuitive, right? You know, if you put a pot of water on the stove and boil this liquid, right? You think there's a lot of, heat around that feels certainly exothermic in our experience. But that's actually an endothermic process to get this liquid to boil. This vaporization is an endothermic process, okay? And it's endothermic because it requires heat being put into the liquid, right? And so you always have to think about these from the system's perspective, where the system here is the liquid in question. So if we have to add energy to the liquid, which we clearly do, we have to put this pot of water on our stove, right, and put heat under it. We are putting this energy into the liquid. The longer we leave that stove on, the more and more energy we're dumping into this liquid. And eventually we'll heat up the molecules, of course, in that liquid enough that they will leave the liquid phase and go to the gas phase. That is vaporization. And so we have terminologies for all these. We could put an ice cube on the stovetop and melt it. Some things will sublime and just go straight from solid to gas, but those are all endothermic processes. The opposite are exothermic, and this is when the system is releasing that energy. And a lot of times, we use energy and enthalpy interchangeably. And enthalpy is really just energy for a constant pressure process. So this is basic thermodynamics. Some of this, should be review. This is a General Chemistry 2 course. These are topics we learned in General Chemistry 1, but we're just reviewing them here as we move towards phase diagram and heating curves. So enthalpy is really just a constant pressure type of energy. And most of chemistry is actually constant pressure when you think about it, right? Our bodies exist in this constant pressure surrounding atmospheric pressure. This water on the stove, there is a constant pressure around it of 1 atmosphere, 760 torr if I'm at sea level. And so a lot of chemistry is constant pressure, so we tend to speak in enthalpy in terms of energy. Anyways, these are the various terms for all these types of phase changes: endothermic, melting, vaporization, sublimation; exothermic, condensation, freezing, and deposition. Now, we have specific terms for the exact amount of energy required to change that liquid water in the pot on the stove to a gas, and that is the heat of vaporization. If you put an ice cube on the stove, how much energy do you have to put in to melt it, to reach the melting point? That is, not to reach the melting point, but to change the liquid to to change the solid to a liquid as the ice cube is melting. That's the heat of fusion. And so this term right here is for our melting, or our freezing, or our fusion. These are all terms that describe this same process of solid to liquid or liquid to solid, right? Heat of vaporization is going to then be our liquid to gas, right? Or gas to liquid would be our condensation, but it's the same energy. It's just a reversible process here that I'm worried about. Heat of sublimation is for solid directly to gas. And so these are quantities you'll come across in chemistry that refer to an actual quantified amount of energy, or here enthalpy, that it takes to complete this phase change, right? Again, this is a physical change, a change of state from solid to liquid, or gas to liquid, or solid to gas. And these are the energies associated. Now, what's really important here is that these energies are going into overcoming intermolecular forces, right? So the energies of heat of vaporization or heat of fusion has to do with overcoming this water molecule's attraction through hydrogen bonding we learned about last time to this water molecule, right? There's an attraction here between these two water molecules to one another through hydrogen bonding. But in order to get, say, these liquid water molecules into the gas phase, these have to be separated, right? I have to overcome this intermolecular force. And that's going to take some energy. Why? Because there's a force here of hydrogen bonding, right? There's a handshake taking place here that I have to disrupt and overcome. So that energy required to break this hydrogen bond, to break this handshake, to pull these two water molecules apart and let them enter the gas phase, where they go careening off into space, that would be my heat of vaporization, liquid to gas. Now, we can compare the quantities here, heat of fusion to heat of vaporization to heat of sublimation, right? All of these terms, the heat is always going to sort of separate the molecules and overcome the intermolecular forces. And we might ask, well, how does the size of these various things relate? And we can ask ourselves then, how does the heat of vaporization relate to the heat of fusion? Okay, so maybe just pause for 5 seconds or so and think, how is the heat of vaporization going to relate to the heat of fusion? Is it going to be greater than? Is it going to be less than? Is it going to be equal to the heat of fusion based on these definitions? So maybe we'll just sort of pause for 5 seconds here or so and think about how these two quantities should relate. Okay, time's up. So let's think about what the answer should be. Heat of vaporization is liquid to gas. Heat of fusion is solid to liquid. So let's think about the physical process here. And going from solid to liquid, these molecules are in this nice, neat lattice. The heat of fusion represents the amount of energy I need to sort of free these molecules up a little bit, to get them to sort of roll past one another. They're still going to stay close to one another. This molecule moves down here. This molecule moves up here. And so they're sort of more sloshy now than they were this rigid crystal lattice before. So you have to input a little bit of energy to break up that solid network and loosen it up into this liquid phase. But think about what you have to do for the liquid to the gas phase. Here, you still have to think about these molecules being close to one another and touching one another, right? And yes, maybe it's a bit more sloshy and things are a little bit chaotic, but what you have to do now is completely separate these molecules from one another and move this water molecule up into the gas phase. Completely break it away from all of these other interactions, these waters that are pulling on it. Okay, so heat of vaporization is pretty much always going to be greater than your heat of fusion, right? Because it's almost always going to take more energy, or enthalpy, strictly speaking, to completely separate the molecules from one another, rather than just kind of loosen them up in the solid to liquid phase. Now, the last thing I want to touch on here is this idea of temperature and energy. Right? You'll notice these are heats of sublimation, heats of vaporization, heat of fusion. These all have the units of energy, or joules. Okay? These are energies that is different from temperature, right? Joules does not equal, right, degrees Celsius or Kelvin. Those are the units we use for temperatures. these are average kinetic energies. Now, what's really interesting about phase changes is that these phase changes don't correspond to a change in temperature, and that's something students often get confused. Okay, so change of state right does not equal change of temperature. And you might say, well, how can that be, right? This pot of water I have on the stove, the heat is getting pumped into it. The burner is glowing red hot. I'm dumping all this heat into this water. Well, at first the temperature is changing, sure. You're heating up the water, but once you get this to 100 degrees Celsius, all the heat you're pumping in is going into this phase change, right? And so while you're changing this phase, while you're boiling the water, stick a thermometer in your boiling pot of water. What you'll notice is that the temperature of the water isn't changing. You're seeing the oven, the stovetop dump so much energy into this liquid water, and it's actively boiling, and yet the temperature isn't changing. So where is that energy going? It's going completely into this heat of vaporization, overcoming all of these hydrogen bonding to liberate the liquid water molecules into the gas phase. Okay, so keep this in mind, adding heat does not always change the temperature. Heat has unit joules, like energy. Temperature has unit Kelvin, and temperature is an average molecular motion. Okay, now, all of this that we've been talking through, whether it's, water on a stove or some other change of state, a lot of times you'll see these on heating curves. Okay, so a heating curve is this, what's pictured on the left here, a plot of temperature versus heat. Again, think of the heat being the stovetop that you turn on and it's glowing red, right? Now, while you're dumping heat, so as we walk to the right on this diagram, we're putting heat into the system, okay? The y-axis is temperature. So notice this first arrow here is when we're heating the solid, okay? So let's think about the experiment of we put an ice cube on the stove and we turn the stove on. What's the first thing that happens? Heat goes into the ice cube and we heat the solid. Right? We're adding heat, so we're moving to the right on this heating curve, heat increasing, but the temperature is going up. So this first part of the heating curve is going up, the temperature is increasing. And so if it's an ice cube, maybe we're starting here actually at, say, -10 degrees Celsius. Right? So -10 degrees Celsius, we put this ice cube on the stove, we're pumping heat into it, the temperature is increasing, and it increases until it gets to 0 degrees Celsius. The stove is still on, it's still adding energy into the ice cube, but now the temperature of the ice cube is not changing. All that energy is going into the melting, right? Into this heat of fusion, this solid to liquid transition. And so now, while we're still adding heat, we're walking to the right on the x-axis here. We're not walking up at all, right? The temperature is not changing. We're just adding heat. All that energy is overcoming the intermolecular forces in the hydrogen bonding network of the solid water. Now, eventually, every single solid molecule of water is loosened up. Enough energy has been added to overcome the heat of fusion. And now, at this point right here, we're all liquid water at 0 degrees Celsius. Okay, so maybe between, we could say A, we wanted to label these, B, C, D, E, F. Okay, we're a solid A, B, and there's still some solid left right before C. But as soon as we hit C, we're all liquid. And now the energy that we're adding is going into heating the liquid, and now the temperature starts to rise. Okay, so now as we get to this point C, and we're still moving to the right, why? Because we still have the stovetop on, it's still adding energy to our system. Now my liquid water that is just a puddle, now perhaps in my pot that is on the stove, now that liquid water begins to increase, and so the temperature goes up, we climb up this line and heat the liquid. And we keep doing that until we get to point D up here. And at point D, now all the liquid molecules have enough energy that we're about to enter the gas phase. And so at this point D, now we are at 100 degrees Celsius. The stove is still on. All the energy we're adding is going into overcoming these liquid-liquid intermolecular forces, and we start to vaporize. The water starts to boil. So you can put a thermometer in this boiling water and see that the temperature doesn't change for this whole amount of time that you're adding a bunch of heat. A bunch of heat is being added here. How much? Well, go down to the x-axis. It's this much. This much minus this much is the amount of heat we're adding. And still the temperature isn't changing because we're overcoming all of those liquid-liquid hydrogen bonding intermolecular forces. Now, we approach point E, and point E is the point where the last little bit of liquid water gets turned into the gas phase, and now we have 100% of our water is in the gas phase. And if this is a closed, vessel, maybe there's a top on the pot of our water, well, the rest of the way that we walk out to the right and heat this thing even more and more, we're just heating the gas. Okay, so you need to understand conceptually each of these parts, how temperature does change and doesn't change at the various parts of this heating curve. And you can find these for different substances. The one I did here was water because, well, we know 0 degrees Celsius is where it melts and 100 is when it vaporizes, but you can do this for any substance. So again, within a phase, the heat is going into changing the phase, not going into changing the temperature. And so within a phase, the heat is the product of specific heat, sample mass, and temperature change. Okay, so the total heat sometimes we call Q, and Q within a phase, right? Within a phase, we're going to have different formula here, so I'm going to sort of outline them. Within a phase, Q is the product of specific heat, which you might see called S. Sample mass, so this is times the mass of the sample, and then times the temperature change. Okay, so I think I misspoke, but this is within a phase, so this is A to B. C to D, or E to F. Within a phase. So A to B, I'm a solid. I am always a solid phase from A to B. From C to D, I am always a liquid phase. From E to F, I am always a gas phase. So within a phase, for those three segments of my heating curve, this is the formula I'm using. And the specific heat usually is joules per gram Kelvin. The mass is usually in grams. And the temperature change will be a change then in Kelvin. And so you can see here that grams, Kelvin, Kelvin. This should be left with joule, which is my unit of heat. Okay, so have some familiarity with the types of units you should be coming across. When you come across problems, maybe you're given kilograms, right? Maybe you're given Fahrenheit. Make sure you're using the appropriate units. Now, these other parts of the curve, the phase changes, the product of the mass and the heat of fusion or vaporization is the heat. So here we're going to use a different formula, okay? So for the phase changes, for these parts, and these parts will be B to C, right? Or D to E. And here my heat is going to be the product of the mass times the heat of fusion or the heat of vaporization. And so the mass obviously is probably going to be given in grams. The heat of vaporization or the heat of fusion, usually you'll have given in joules per gram. Now, sometimes this instead will be given in moles, or you'll have to convert, or this will be given in joules per mole or kilojoules per mole. So don't be alarmed if you see moles instead of grams or kilograms instead of grams. I ultimately know from dimensional analysis that the things you multiply together must give you joules in the end. Okay, so when you get these heat of fusions or heat of vaporizations, right, any of these things here, they're usually in joules per mole, joules per gram, kilojoules per mole, kilojoules per gram, for example. Now, That's our heating curve. This has all been very conceptual. Now let's try to put this into action and actually solve a problem, right? Based on some given information and what we want to do. Now, these heats of fusion vaporization, as we talked about before, are different numbers, right? The heat of vaporization, as we talked about here, is pretty much always going to be greater than the heat of fusion. In the same way, these specific heats, right, this C term right here, is going to be different, so pay attention, whether you're a solid, liquid, or gas. Remember, this formula here is when you're in a given phase, right? And so you want to make sure if you're in segment A to B here, which is the solid phase, you're using the specific heat of the solid. Okay, or if you're C to D, you want to make sure it's the specific heat of the liquid, right? Or if it's E to F, then it's the specific heat of the gas phase, right? Because the specific heat has something to do with how much energy do I need to absorb to change my temperature. And that very much has to do with the intermolecular forces, the density of the material, how close the molecules are, and that changes from solid, liquid to gas. So, all that said, let's try to solve this one. What is the enthalpy change required to convert 10 grams of ice at negative 50 degrees Celsius to liquid at 50 degrees Celsius? And so a lot of times for these problems, I'm going to work it out here, but a lot of times for these problems, it really helps to draw this heating curve. So that would be my first suggestion in these types of problems when you're trying to calculate the amount of heat or the enthalpy change required to convert some, solid to liquid or solid to gas or liquid to gas. You're going to need obviously some of these constants we talked about, specific heat, heat of vaporization or fusion, but it makes it a lot easier if you draw a diagram. So let's think about the diagram we would need here. And we're just going to draw something similar to what we had before, only much poorer in quality. Here's heat added on the x-axis. Here's my temperature on the y-axis. And where am I starting here? What is the enthalpy change required to convert 10 grams of ice at negative 50 degrees Celsius? So here I'm starting at negative 50. And I want to go to liquid water at 50 degrees Celsius. We could probably put this a bit higher here. Move this a little bit. This is temperature. This is 50 degrees Celsius. But I know something about water that it's probably pretty important that I go through 0 degrees Celsius. Right? And so starting at my point, we'll say A here. I have to take this solid ice at negative 50, and I'm going to have to add heat and get it to increase to 0 degrees Celsius. Right? That's my A to B transition here, heating up the ice. B to C, this is pretty flat, or should be. And B to C here is staying at 0 degrees Celsius. This is overcoming all the solid intermolecular forces and melting the solid ice to liquid water. But then I'm not done because I'm still at 0 degrees Celsius. Last, I have to increase the temperature of this now liquid water up to point D to get it to 50 degrees Celsius. So I need to calculate the energy involved, the Q here, which will also be equivalent to my enthalpy at constant pressure for A to B, for B to C, and for C to D. Right, these three things. So I should have 3 calculations here. Now, obviously I need some information. I don't have the specific heat memorized for water. I don't have, well, actually I do, but you might not. I might not have the delta H vaporization or delta H fusion memorized. So you would have to be, on an exam given these numbers, or you have to look these up in a table in your book. Just again, make sure you're looking up the appropriate specific heat and the appropriate delta H that you care about. So let's think about the amount of heat Q for A to B. Okay, for Q A to B, what formula am I going to use? Well, here I'm within a phase, I am just the solid. I need specific heat times mass times change in temperature. Right, so I need the specific heat of the solid times the mass times the change in temperature, delta T. Now, you can look it up in a table. My table for the specific heat of water in the solid phase is 2.09 joules per gram Kelvin or gram Celsius. It actually doesn't matter because we're dealing with a change in temperature here, and that change in temperature won't matter if it's Celsius or Kelvin since those differ by 273. It's the net difference that matters. It's going to be the same number here. So it doesn't really matter if it's joules per gram Kelvin or joules per gram Celsius for these examples. I also need the mass here. Well, I'm told it's 10 grams. And then I need the change in temperature. Remember A to B, final temperature 0, minus initial temperature negative 50. So that comes out to positive 50. And so I have 2.09 times 10 times 50, and I should get 1,045 joules here. So that's for the first step, A to B, just heating up the ice cube. Right? You could see if this was, 0 degrees Celsius, 273. If this was Kelvin, 273 minus 223 Kelvin, it would still be 50 here. So again, it doesn't matter actually if you convert to Kelvin or Celsius here. It's about the difference. It's a linear relationship. So no need to get too scared there. Now, if it was degrees Fahrenheit, then you're going to have trouble, right? Because these are usually degrees Celsius or degree Kelvin. So pay attention for that. That is just step 1, A to B. Step 2, B to C, I need a different formula, right? Because here I'm undergoing a phase change, and we learned that means it's mass times heat of fusion. But let's throw a little wrinkle in here. Let's say the only heat of fusion I have access to, right? And maybe I look at my delta H's. There's a delta H vaporization. I don't want that. Why not? Because I'm not doing liquid to gas. There's a delta H of sublimation, but I'm not doing solid to gas. Don't want that. I want the one that is delta H fusion. That's the one that's related to solid to liquid. And let's say for delta H fusion, I look it up and my delta H fusion here is 6.01 we'll say kilojoules per mole. That's my delta H fusion, right? And my formula here is my delta H. Well, I said times mass, but it might be in joules per mole or joules per gram. I'm given here a heat of vaporization in kilojoules per mole. So I can't just put my mass here 10 grams because that's not going to work out and cancel there. What I need to do is convert this 10 grams to moles. All right, so pay attention to your units here. You can go through and actually convert 10 grams to moles. I hope you can. The molar mass here, we'll just use 18 grams per mole for water, and I get a amount of moles of 0.556 moles of water. So that's what I want to use here because that is my amount of water. Multiplying these out, I get 3.342 kilojoules, right? I'm paying attention to my units here. I started with kilojoules, I'm left with kilojoules. You could convert the kilojoules here to joules, right? Or you can do it at the end. I'm going to do it at the end here and multiply by 1,000. So I get 3342 joules. That's step 2. 1, 2, and now we're at step 3. Step 3, this last Q going from C to D is going to look a lot like the first one, only I need to pay attention that this heat capacity here, or this specific heat rather, I'm using the correct one. I'm in the liquid phase, so make sure you use the specific heat of water in the liquid phase. This is one I have memorized, 4.18 joules per gram Celsius. This times the mass. And this times final temperature 50 minus initial temperature 0. 50 times 10 times 4.18 gives me 2090 joules at the end. And so in total, the total enthalpy change, it's not working, the total enthalpy change is 1 plus 2 plus 3 those processes, not those numbers. That would be convenient. 1045 joules plus 3342 joules plus 2090 joules for a grand total of 6477 joules. If you worry about sig figs here, I think you have to round it to 3 actually, and we could put it at perhaps kilojoules, 6.48 kilojoules, right? Or 6,480 joules. That is my total enthalpy change for this process. And it gives you some perspective for just 10 grams of ice, which is not a lot, how much heat you have to actually pump into this to free up the solid water, to get it to start moving with a kinetic energy of 0 degrees Celsius, to melt that solid water to liquid, and then to heat up the liquid water to 50 degrees Celsius. Quite a bit of energy for just 10 grams of water. So, in this lecture, we covered these heating curves and these phase changes, and did some practice problems here of the amount of enthalpy involved in these phase changes.